Now we want to look at periodic trends in ionization energy and electron affinity. And we're going to define these terms very carefully. They have to do with the energy related to forming ions, either cations or anions. And you can read about this in sections 4 and 5 of chapter 7. We'll start with ionization energy. Ionization energy, which I will abbreviate capital IE, is the energy cost to remove an electron from a gas phase atom or ion, and it's important that you understand that gas phase is part of the definition. So implied by this definition is a chemical equation, and I always ask students to write down chemical equations for these definitions on the ensuing test, so know how to write the chemical equation associated with this. Here's a sample chemical equation where M just stands for some generic metal, typically because metals form cations. It's not any element in particular. A gas phase atom loses an electron to form a +1 gas phase cation. The change in the energy for this process is what we mean by the first ionization energy, denoted IE sub 1. So if we form IE10, the 10th ionization energy, that's the formation of a cation with a 10 plus charge. We'll never encounter something like this, but in principle, this is how you would write down the defining equation, forming the 10 plus cation in the gas phase from the 9 plus cation, not from the neutral species. Ionization energies always involve the loss of individual single electrons. Let me emphasize, these state symbols are absolutely mandatory because the definition says it's from a gas phase species. You have to remember that. I'm not going to remind you when I ask you for this on the test. Let's look at some data for ionization energies. Here's a table from the text showing successive values of ionization energies for a variety of elements. Now, if we look at the data, we see some interesting trends. So for example, let's just pick aluminum. I1, they use I instead of IE. They still mean ionization energy. So removing the first electron costs 578 kilojoules per mole of aluminum. Removing the second one costs a lot more energy. Removing the third one costs even more energy. There's a general trend, no matter which element you pick, the ionization energies always increase. So that's one of the observations. It takes more energy to remove each successive electron. This shouldn't be a big surprise, because as you remove each electron, you're leaving behind a more positively charged cation, and it's got to be harder to pull an electron away from an aluminum plus than it is to pull one away from an aluminum with a neutral charge. Secondly, this stepped line that we see in this table indicates when you've removed all of the outer electrons and are starting to remove electrons from the underlying noble gas core electrons. And we see that for sodium, removing one electron costs nearly 500 kilojoules per mole, but removing a second electron is a prohibitively expensive operation in terms of energy. It costs 10 times as much energy. For magnesium, it costs twice as much to remove the second electron, but jumping to a third electron, again, that the order of magnitude of the change in the ionization energy is huge. This is really the experimental evidence for what we mean when we say noble gas electron configurations are particularly stable. If you remove the outermost electron, it costs energy, but breaking the electron configuration of the underlying noble gas is prohibitively expensive. We never see it happen in chemical reactions, and this is why. Sodium only forms a +1 cation, never a +2 cation, because it's energetically inaccessible. Magnesium, an alkaline earth, forms a +2 cation, but never a +3 because it costs too much energy. Aluminum can lose 3 electrons, but never 4. So there's a huge jump in energy when removing an inner core electron. Now let's look at the periodic trend in ionization energies. The horizontal trend is that ionization energy increases left to right. The vertical trend, ionization energy decreases top to bottom. Why? What are the reasons? Well, within a period, going left to right, remember, we've already seen effective nuclear charge gets larger left to right. Well, having a larger effective nuclear charge means it takes more energy to pry an electron away from this atom. It's being held more tightly by that larger effective nuclear charge, and that's the reason for the horizontal trend in ionization energy. Within a group, for the vertical trend, remember the effective nuclear charge doesn't change very much in a vertical trend, but outer electrons are in much larger orbitals, and so they're very much farther away from the nucleus, and for that reason they are easier to remove. That's the reason that ionization energy gets smaller in the vertical trend as you go from top to bottom on the periodic table. We see those trends reflected in this figure from the textbook. If we go from top to bottom, we see a general decrease in ionization energy. If we go left to right, there's a general increase in the ionization energy. And again, if you look very carefully, there's some exceptions to these trends, and they're worth thinking about. They're interesting features when there's exceptions. Nonetheless, the general prediction is increase left to right and decrease right to left. Now let's look at the process of forming anions instead of cations. This involves something called an electron affinity. Now the English word affinity simply means attraction for, so this phrase should in your mind be some sort of measure of the attraction for an electron. It's sort of like the opposite of an ionization energy in the sense that this is the process of forming an anion as opposed to forming a cation. So the technical definition then of electron affinity is the energy change. Right now, as soon as I see energy change, I know electron affinity is going to have units of energy because it is an energy change associated with adding an electron to, once again, a gas phase atom or ion. So let's see some examples. Again, using a generic symbol A. There is no element A on the periodic table. This is just a placeholder for any element. The chemical equation associated with the definition of electron affinity is this equation here, where we have a gas phase atom. We add an electron to it to form a gas phase anion. The energy change in this chemical reaction is what we mean by an electron affinity. So equivalently, if I were to write down the chemical equation for the fifth electron affinity of something, that would be forming the fifth negative charge something in the gas phase by adding one electron, not five, one electron to the 4- charge of the corresponding substance. Now it turns out that electron affinities, being energies, are almost always negative for atoms and always negative for cations. That means that as you bring the electron up close to an atom, it feels an attraction. Why is that? Well, the reason it feels an attraction, of course, is due to ineffective shielding. I'll say inefficient shielding. That is, even though the atom itself in the gas phase is electrically neutral, as an electron approaches it, it will still feel a little partial nuclear charge from the nucleus because the electrons in between it and the nucleus don't completely shield that charge. So if we look at periodic trends, electron affinity trends, the general trend is it becomes more negative left to right. So fluorine has a much larger negative electron affinity than oxygen. And unfortunately, there is no real reliable vertical trend. So if we're comparing atoms in a vertical trend, carbon has a larger negative value than germanium, but smaller than silicon. It's just not very reliable. So we don't use a vertical trend for electron affinities. And you may even notice, once again, there's sort of exceptions. This whole group seems to be an exception. You might want to think about why that is. But as a general trend, electron affinities get more negative, minus 27, minus 122, minus 141, minus 328, left to right. And of course, it's somewhat meaningless for noble gases, which don't form anions.